In this video, we are going to be talking about ionization energy, and more specifically, the periodic trend of ionization energy and how it relates to the different locations of atoms on the periodic table. So first of all, let's just talk about electrons. They are sort of flying all over around in an atom, and what we are going to focus on in this lesson specifically are the valence electrons. So those outermost electrons. So in this sodium atom, this picture of a sodium atom, sodium has one valence electron, and that electron is in the third energy level. Now you might remember that if we add energy to an atom. So we're just adding some energy to an atom, whether it be light or heat or some sort of radiation, we're adding energy to an atom. So what happens when we add energy to an atom? What happens to the electrons? Well, you might remember that if you add energy to an atom, the electrons bounce out to outer shells. So they bounce out to outer shells. And then we all remember, hopefully, that when they are out in those outer levels and those higher energy levels, they don't stay out there permanently. They fall back down, releasing energy. But what happens if you give an atom too much energy, or if you give an atom a lot of energy? Well, what happens to those electrons? They don't just bounce out to outer energy levels anymore. They leave the atom altogether. So if we give an atom a lot of energy, we're increasing the amount of energy we have here, that electron, that valence electron, can just leave altogether rather than bouncing out to an outer energy level. Now the amount of energy it takes to steal an electron away is called the ionization energy. So the ionization energy is the amount of energy needed to remove an electron from an atom. Not just any electron, but a valence electron from an atom. So it's possible to steal an electron away from an atom. And remember, that amount of energy it takes to steal an electron is called the ionization energy. And it's different for every type of atom. Now, for some atoms, it's really easy to steal that outer electron away. So if it's very easy to remove that outer electron, that would mean that that atom has a low ionization energy. Think about your daily life. If a task is easy to complete, that generally means that it requires very little energy. Now, on the other hand, if something is very difficult to complete in your daily life, then it requires a very high amount of energy. So for some atoms, it's really hard to steal that outer electron away. So it's going to require a great deal of energy. So for some atoms, they have a very high ionization energy because it's very difficult to remove an outer electron. So every atom is different, and every atom has a different ionization energy. Now for the rest of this lesson, we will focus on the trend in ionization energy. Now remember, a trend is just a general pattern. It's a way of predicting what might happen based on given information. So let's look at the trend for elements in the same group or column on the periodic table. We have group 1 here. Now hydrogen, you'll see, has one valence electron in that first energy level. Lithium has one valence electron, but it's in the second energy level. And sodium has one valence electron, but it is in the third energy level. So we will be talking about how much energy, or the relative amount of energy it takes to remove each of these electrons. Now, which electron do you think would be the easiest to remove? One that is really close to that positive nucleus, pulling it in, or one that's very far away from the nucleus that would be pulling it in, that positive nucleus that would be pulling the electrons in? Well, it turns out that the farther an electron is away from the nucleus, the easier it is to remove. Think about two magnets. If you have two magnets that are touching and you try to take them apart, it's very difficult to, if they're strong magnets, it's very difficult to take them apart if they're touching. But if you start with the magnets a couple inches away or a little space away from each other, then it's easy to separate them because they're already separated somewhat. You just have to take it in the extra bit. So as they get closer and closer and closer together, it becomes more and more and more difficult to separate them. So atoms that are bigger are going to have electrons farther away from the nucleus, which means it's going to be easy to remove those outer electrons, which means they're going to have low ionization energies. And electrons that are very close to the nucleus, so in smaller atoms, they're going to have high ionization energies because it's going to be more difficult to remove an electron that's very close to the nucleus. So as you move from top to bottom on the periodic table, the ionization energy of an atom decreases. And the reason for this is because valence electrons, so those outer ones that are leaving, they're in higher energy levels farther away from the nucleus. Now if we look at elements in the same period, so this is the same row. We have lithium, beryllium, this row here, the second row of the periodic table. One thing I want you to notice is that every single atom in this row has 2 energy levels. So the outer electrons are going to be about the same distance from the nucleus. Hopefully you remember though that nucleus pulls in the electrons. So the stronger the charge on the nucleus, the more positive it is, the more it pulls into the center. So you'll see that those atoms, as we move across the periodic table, those atoms tend to get smaller and smaller and smaller as we move from left to right. So you'll also notice that I have shown you the number of protons. We have 3, 4, 5, 6, 7, all the way across to 9 in that second row. So we're increasing the number of protons. And what this does is this creates more pull to the center, which creates smaller atoms, and you can see they're getting smaller and smaller as you move from left to right. And what this does is it makes it more difficult to remove electrons from those outer energy levels, which means that we have higher ionization energies. As we move from left to right, the ionization energy increases. Now, if you think about that pull being a magnet, in lithium we would have a weaker magnet in the center, a weaker pull because there's only 3 protons. And if we look all the way to fluorine, we have 9 protons, so we have a much stronger pull toward the center. It's like a stronger magnet pulling those electrons in. Now if we look over to the left-hand side, over by lithium, we have less protons, so there's going to be less pull, which means we're going to have bigger atoms, which means it's going to be easier to remove electrons, which means we're going to have a lower ionization energy. So the lower ionization energies are going to happen at the left side and the higher are going to happen at the right side. So here we go. As we move from left to right on the periodic table, the ionization energy of an atom increases because valence electrons, even though they're in the same energy levels, the nucleus has a greater effective charge. So really what that means is we have more protons in the nucleus, and those protons will be pulling in the outer electrons. Also think of it like this. Elements on the left-hand side of the periodic table, they want to lose electrons because their nearest noble gases have fewer electrons. So lithium's going to want to lose that one outer electron. It practically will give it away. It requires such a little amount of energy to give up that outer electron. It wants to lose it. But fluorine has 7 valence electrons. It does not want to get rid of any. In fact, it wants to gain a valence electron because then it would look more like the noble gas next to it. It would have a stable, full outer shell. So that fluorine doesn't want anything to do with giving up electrons because it's trying to go find one to complete its outer shell. It doesn't want to take a step backwards and give up an electron when its purpose is to try to find one. So on the left, we have atoms giving up electrons very easily, which means it has a low ionization energy. And on the right side of the periodic table, we have atoms that want electrons. So they're not going to want to give up the electrons they already have, which means they'll have a higher ionization energy. Now, once sodium has gotten its ionization energy and that valence electron has been removed, now it has a complete octet. So it's very stable. And the next innermost layer would now be the valence shell. So it has a full valence shell. And sodium, when it loses that electron, it has the same valence shell or the same electron configuration really as neon, which means it has a full outer shell, which means it's completely satisfied. So what if you want to remove another electron from sodium? Well, this is where we look at the second ionization energy. So the first ionization energy, the amount of energy it takes to remove that first electron from sodium, is about 500 kilojoules per mole. Now, if we want to remove another electron from sodium, keep in mind, by now it's happy. It has a full outer shell. It looks just like neon on the outside. It requires almost 10 times as much energy to remove an electron from that octet. It requires about 4,600 kilojoules per mole because it was already happy and now you're trying to remove an electron from a stable, full outer shell. So the first ionization energy is the amount of energy it takes to remove one electron, and the second ionization energy is the amount of energy it takes to remove two electrons, and so on down the line. There are ionization energies for every quantity of electrons that you want to remove from an atom, and all those ionization energies are different.